Hello everyone, myself Somenath Mondal, PhD research scholar working in Indian Institute of Technology, Bombay, India. Today I am presenting my research work entitled as Modeling of Heat Migration through Soil Mass. I have conducted a part of my research work in Equal Response Paris Tech, Paris, France, as a part of GREAT project, which is sponsored by European Union Commission. My GREAT second period was October-November 2015. My supervisor at Home Institute is Professor D.N. Singh, and my supervisors at Host Institute were Dr. Jean Michel Pereira and Dr. Anne Min Tang. First of all, let's see what happens when a soil mass or a soil matrix come in contact with thermal energy. Let's consider a matrix of soil mass which consists of several water molecules which are prevailing in the pore space inside the soil particles. Now see what happens when thermal energy comes into contact with the soil mass surface. Now heat energy will be conducted through the soil particles towards the deeper zone of soil mass. In the process, the moisture or the water molecules which are prevailing just adjacent to the soil surface will get evaporated, and the water molecules which are prevailing just beneath the zone deeper than the surface or in the subsurface zone will be having a tendency to go away from the heat source. So that way a difference in degree of saturation will be created inside the soil matrix. That would result in developing thermal cracking in the soil mass. This kind of thermal cracking would result in failure of several civil engineering structures. So it becomes necessary to understand how heat energy migrates through the soil and what would be the critical moisture content after which that soil will start cracking. In this context, let us see what are the possible ways heat energy can migrate in the soil particles which is in saturated or partially saturated condition. Now, if we enlarge 3-4 particles of a soil matrix, and we can see that there are 3 soil particles, and adjacent to that we have water molecules. Now first of all there will be a particle-particle conduction. Next there will be a particle-to-particle contact conduction. Followed by that there will be a particle-fluid particle conduction. Next would be a particle-particle radiation. Number 5, there is a possibility of particle fluid conduction, and then pore fluid conduction. Number 7, pore fluid convection, and number 8, radiation. As of now, by the previous researchers, it has been considered that heat energy transfers through the soil mass predominantly by conduction. But what are the different kind of conduction and how much they are contributing in overall transfers of thermal energy? That part yet to be explored. So it necessitates a study in understanding the heat migration mechanism in soil mass. As a fundamental research, this study has immense application in different fields of environmental geotechnology, such as design of nuclear and thermal power plant waste disposal system, design of rocket launching pad, design of cross-country pipeline and underground crude oil storage tank. Now let's see what would be the mode of heat dissipation from a oil carrying pipeline or a underground crude oil storage tank. Here we can see that the direction of the arrow describes the possible way of heat migration through the soil from that particular structure. Number 4, foundation design of furnaces, boiler unit, brick kiln, etc. Here also from the diagram you can see the possible direction of heat migration or heat dissipation from that kind of structures. Now power design of buried electrical conduits. This study plays a very important role in understanding and designing the power of a buried electrical conduits. Now let's consider a buried circular sections conduits. Now the moment electrical energy starts transferring through these conduits, because of the inherent resistance of this particular electrical conduits, it will start heating, and that heat energy will be migrating radially from the buried conduit, and the maximum power of these buried conduits will be depending upon the thermal properties of the adjacent material of the buried conduits. Next would be underground explosion, and last geothermal energy. Now these are the all different civil engineering or let's say geotechnical engineering structures which are thermally active. Now in all such cases, either we want heat energy to be dissipated from the away from the structures, or we want heat energy to be limited in a particular zone adjacent to a particular structure. Now to design all these things as per our demands, we have to understand first the fundamentals of the heat migration. Before starting the heat migration study, it is necessary to understand the thermophysical characterization of the materials which have been considered for the study in terms of thermal conductivity, thermal resistivity, thermal diffusivity, and specific heat. Now for doing that, a transient probe was employed. Before using that probe, it was calibrated using a material of known thermal resistivity. For our study, glycerol was used for calibration purpose, and the voltage which we got from the calibration was 0.5 volt. Employing this single needle transient probe, we have got thermal resistivity, thermal conductivity, diffusivity, and specific heat value of two different soil S1 and S2 for four different dry density. These particular properties of the material tell the potential of those soil samples in terms of thermal response. Now, as per the objective to study the heat migration mechanism through soil in terms of thermal flux and temperature over a period of time, a methodology has been developed named as thermal flux method. Now, four thermal flux sensors are employed to conduct these particular methods to obtain the thermal flux and the temperature over a period of time of 12 hours. Now, a 20 centimeter deep and 15 centimeter by 15 centimeter section mold, perspex mold, was taken for this study, and it was filled, maintaining the uniformity in the packing density of the material, and very carefully all those flux sensors and thermocouple are placed in the desired depth to monitor thermal flux and temperature for the total period of applied heat. Now, to establish a perfect steady state system, the bottom of the mold was taken as an aluminium base of having higher thermal conductivity. Now, this photo shows the thermal flux which was employed to establish heat migration in the soil mass. By using these particular methods, the thermal conductivity of the material was also calculated by considering this particular section and employing this particular relation of one-dimensional steady state heat conduction. Now let us see the thermal flux profile and temperature profile which has been obtained from these methods. Now the figure which is there in the left side, it shows the change in flux over a period of time, and the figure which is situated in the right side shows the temperature profile over a period of time. Now it's very evident from the flux profile figure is that the system comes to a steady state at around 400 minutes of the starting of application of heat energy, and after that ideally all flux profile should be linear, but because of some manufacturing limitation of the thermal flux sensors, we have observed a band of thermal flux profile in the figure. However, this portion of the particular flux versus time graph should be considered as a single line. Now if we see the temperature versus time profile, the same thing is getting depicted over here. We can see around 400 minutes the temperature is coming almost linear and parallel to the time axis, which depicts that there is no change in the temperature with respect to time. So this establishes that the system has reached to a steady state after 400 minutes. Next, to validate the thermal flux and temperature profile which have been obtained by employing the thermal flux method, a simple finite difference model has been developed based on the explicit solution. Further, the finite difference model was validated by comparing the results obtained from an analytical model which has been developed based on Laplace transform, as the experimental problem as well as the mathematical model is a one-dimensional heat transfer problem. So to develop analytical model, one-dimensional heat conduction equation through solid was solved. Finally, a finite element model has been established employing COMSOL to compare and validate the results from experiment as well as from the finite difference model. Finally, a very well match was found in the results between finite difference modeling and COMSOL modeling with the results obtained from experiment. These are the future studies which are being proposed. Number 1, the heat migration mechanism has been established by using thermal flux method. However, the reproducibility of the results has to be checked. Next, now the study of heat migration through fine-grained materials has not been performed. So, the heat migration study through fine-grained materials in different degree of saturations are being proposed. Next would be the study of heat-induced moisture migration, which is a coupled phenomenon, has to be studied, and one of the possible way would be by employing miniature moisture sensors in the mold which has been developed and described in this particular study. And last, the correlation of the material specific inherent parameters or properties with its thermal response have to be studied. There are several studies which are existing in the literature where several researchers have mentioned the influence of several material specific parameters, but most of the studies are qualitative studies. Hence, a quantitative study is required to establish a correlation between the soil thermal response with its material specific parameters. Thank you.